Hey folks, let's talk about orbitals and electron configuration today. The question we really need to answer is, where are the electrons? We know from photoelectron spectroscopy that the electrons are arranged in shells and subshells. And that's awesome, but it doesn't really provide the predictive power that chemists want. And so a lot of time was spent trying to tease out a little more information about where you actually find those electrons. And that's taking information from PES and a lot of cool mathematics and theory and trying to mesh the two and make everything match up with a whole host of experimental results. So what do we know now? Where have we come to? We have decided that Bohr's idea of orbits, and so if you draw the PES pictures with little circles, is a little simplistic. The electrons are not actually in nice, neat little racetrack orbits. Instead, electrons are found in orbitals, which are regions of space where an electron will have a particular energy. And I say it's a region of space because it's not always the same shape. We'll talk more as we get going, but there's a lot of different shapes that an electron can be in that might have the same energy. So these orbitals where we find our electrons are indeed organized and grouped into shells and subshells. Let's talk about the shells first. The shells that the orbitals are organized into are actually going to be numbered 1, 2, 3, 4, and so on and so forth. And the larger the number of the shell, and so we're going to say n equals for the number of the shell, the larger the number of the shell, the farther those electrons are from the nucleus. And if they're farther from the nucleus, it turns out they're actually just larger regions of space. So that's the first thing. It's also good to be said that the actual energy of those orbitals in those shells does increase as you get farther away from the nucleus. They just have greater potential energy. So you've got these shells. Now we also have subshells. So the subshells we're actually going to give letters to. And the subshells that are occupied that we see in the elements on the periodic table are S, P, D, and F. Okay, the letters are historical, so just roll with that. Now, not every shell has all of these subshells. It turns out that the first shell is pretty close to the nucleus, so it only has space for one subshell. It just has an S. And then as you get to the second shell, there's space for an S and a P. Third shell, you get an S, a P, and a D. Fourth shell, you get an S, a P, a D, and an F. You get the idea. Every time you add a new shell, you can add a new additional sublevel to that shell. Each of these subshells actually has a different shape. And so the electrons are occupying a different shape. And this is just downright cool. S subshells, all of the subshells, regardless of the energy level that it's on and the shell that it's in, they're all spherical. So I'm going to draw you a cute little sphere. And then I'm going to actually show you what these look like with someone who can actually draw better than me. So this is ptable.com, and they have a really neat tab up here called Electrons, and on that you can actually see what all the different orbitals look like. So if I click on, say, a 1s orbital, you'll see over here that a 1s orbital is spherical. If I click on a 3s orbital, it's also spherical. They've got a little wedge cut out so you can look on the inside, but the idea is that those are spherical. P orbitals are interesting. They are going to be kind of a dumbbell shape or like to have two lobes. Again, my three-dimensional drawing is a little shaky, so let me show you some pictures here. So if I click on a P orbital, you'll see that it's got two lobes to it. And there is actually 3 different orbitals that all have this same shape and so are given the designation of P, and they just point in different directions. If I take a look at a D subshell, what those orbitals look like, these we often describe as a cloverleaf. Most of them are cloverleaf shape. But again, here I've got more than one orbital that has this same designation, this same energy. And so these, you'll see this one's the one that's different. We say it has a belly band. But in general, these are kind of our cloverleaf shape. So I'll draw that for in your notes. Try to do 3 dimensions. And there are 5 orbitals that have this shape and would go into a subshell for the D subshell. F's, well, F's are complicated. So here's a picture of an F. Oftentimes we're described as a double cloverleaf. I'm not even going to pretend I can draw that. I'm just going to write complicated. But it turns out there are 7 orbitals that can fit into an F sublevel, a subshell. And these have various shapes that are complicated. But the big take home at this point in time is that our electrons are actually found in regions of space that have a variety of shapes, are found in regions of space that we call orbitals. And we can organize those orbitals into shells and subshells. And that tells us something. The shells tell us about their size and relative energy. And the subshells tell us something about the shape of that space that those electrons are in. And also, it's worth noting and remembering that you can have more than one orbital in a particular subshell. There's one last thing you have to remember about orbitals, and this is important. What you need to remember about orbitals is it told you it's a region of space where electrons have a particular energy. You can only fit 2 electrons into each orbital. So there's a maximum of 2 electrons per orbital. So these are the places we can put our electrons. What we're going to turn our attention to now is how do we keep track of where the electrons would be for any particular element, and how do we tell someone about that? This is an orbital filling diagram. It is a way to summarize what orbitals there are, their relative energies, and where we're going to find our electrons. So as you look at an orbital filling diagram, each line represents an orbital. So you see that there is a 1s orbital that's available. There is a 2s orbital. There are 3 orbitals that fill the 2p subshell, and so on and so forth. So each of those lines represents an orbital, and we label them so we know which one we're talking about with our letters and numbers. When we go to put an electron into an orbital, we are going to do so by drawing a little arrow. And traditionally it's kind of a fish hook, so it's a half an arrow. And our arrows can either point up or they can point down. And those represent the 2 different electrons that can fit into an orbital. Because electrons have this thing called spin, and it's just a property of the electron. And I told you could fit a maximum of 2 electrons per orbital. One has to go spin up, one has to go spin down. So let's take a look at the rules for placing electrons into these orbital filling diagrams, because there are 3 of them that will help us along the way. Okay, here are your 3 rules. First, the Aufbau Principle. It just says put the electrons in the lowest energy orbital that's available, that's not already full. That's the first thing. Second, Pauli exclusion principle. Like I just said, you can fit a maximum of 2 electrons per orbital. One has to go spin up, one has to go spin down. Third rule, when you get to orbitals like the 3p, where you've got multiple orbitals in the same subshell and so they have the same energy, you need to put your electrons in singly. So you spread them out before you go back and start pairing them up. And you want to make sure you're maximizing spins pointing in the same direction. So you'll fill them all spin up and then go back and fill them all spin down. Let me show you how we use these rules. So let's say we take the element oxygen. Now, when you look on the periodic table, oxygen's atomic number is 8. So it has 8 protons and 8 electrons in a neutral atom. I'm going to take these 8 electrons, I'm going to start putting them into my orbital filling diagram. The first 2 will go into the lowest energy orbital available. That's the 1s. The next 2 go into the 2s. And then when I get to the 2p, I'm going to put an electron into the 2p. That's my 5th electron. My 6th one will go into the next 2p orbital. And you just spread them out. Since those orbitals have the same energy, I want to try to keep my electrons as far apart as possible so they don't repel one another. So that means I've used 2, 4, 5, 6, 7 for my next electron. And then I have to now pair this up because these orbitals aren't filled. So my 8th electron goes spin down back in my 2p orbital. That's it. That's the process of putting electrons into an orbital diagram. Let's do one more. So let's pick something, say, like titanium. So titanium has 22 electrons and 22 protons. 22. Okay, here we go. 1, 2 go in the bottom orbital. 3, 4, 5, 6, 7. Note I'm putting them singly in, and then I'm going to double up. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now look carefully. The next orbital in terms of lower energy is the 4s. So I'll put 19, 20, and now I get to my 3d, which has just a slightly higher energy, 21, 22. Done. So orbital filling diagrams, count your electrons, drop them in, bottom up. Orbital diagrams are great, but they take a lot of space to write. So we want a shorthand, and so we have what's called electron configurations, which is a shorthand way of conveying this information. All you're going to do is summarize which orbitals have electrons in them and tell someone how many. So starting from the bottom up, just like we fill, I would say my 1s orbital has 2 electrons in it. And this superscript is my number of electrons that are in that orbital. And then I go to the next higher energy orbital, which is the 2s, 2s2. And then I get 2p. There's 6 electrons total in the 2p subshell. And then I get 3s2, 3p6, 4s2, 3, 2. And so you're summarizing your orbital diagram with this electron configuration, which is nice because it takes less space. So in summary, orbitals are regions of space where you will find electrons, and they are organized into shells and subshells that have different sizes and different shapes, and in subshells you can actually have more than one orbital. We can take and use an electron filling diagram to show where the electrons are for a particular element, and then we can use a electron configuration to summarize that information. Just remember, when you're using your diagrams, fill from the bottom up, max of 2 electrons, 1 spin up, 1 spin down per orbital. And when you get to orbitals in a sublevel, in a subshell that have the same energy, fill those singly before you come back and double them up.